Welcome to another informative series on transmission line. In today's video, we will be analyzing power transmission lines using another method, which is known as Nominal Pi method. So without any further ado, let's get started. Nominal Pi method is usually used to analyze medium transmission whose length is more than 80 kilometers and greater than 69 kilovolts. If you want to find out more about the characteristics of these lines, you can check our previous series for that. Now back to the video. In Nominal Pi, the capacitance of the line is usually localized at both ends of the transmission lines, that is, one of the capacitance at the sending end and the other one at the receiving end, while the impedance will be lumped at the middle of the line.
That said, this method can also be known as the split condenser method, which is because of the way the capacitance is localized within the circuit. That is, one at the sending end of the lines and one at the receiving end of the line, while the impedance are lumped at the middle of the line. Now let's look at the features this method has over the nominal T method. 1. In terms of simplicity in circuit analysis, the Pi model simplifies the analysis of transmission lines, most especially for medium-length lines where the effects of capacitance and inductance need to be considered. With these, it makes it easier for us to calculate voltage drops, current flow, and power losses.
2. In terms of distributed parameters, transmission lines usually have distributed parameters all over the lines, such as resistance, inductance, and capacitance, rather than lumped parameters. The Pi model makes it possible to effectively capture these distributed effects by representing the line with series inductance, resistance, and shunt capacitance.
3. In terms of voltage and current relationships, the Pi model allows for straightforward calculation of the voltage and current relationships at both ends of the transmission line. The model divides the line into two halves, with shunt capacitance at both ends. This makes it easier to analyze under different loading conditions.
The fourth feature, in terms of frequency response, the Pi model is particularly useful for analyzing the frequency response of transmission lines. With these, we can understand how transmission lines behave under AC conditions, which include resonance and impedance matching.
5. Just like you said earlier in terms of the length of the line. The Pi model is the best approach in solving medium transmission lines, which is because it provides a good balance between accuracy and complexity.
6. In terms of capacitive effects. The shunt capacitance in the Pi model allows for the inclusion of capacitive effects, which are significant in long transmission lines. This is important for accurately predicting the behavior of the line under various loading conditions. And Ferranti effect can also be analyzed better in Pi model, which is due to the way the capacitance are arranged within the circuit.
In summary, the Pi model provides a practical and effective way to analyze the electrical characteristics of transmission lines by capturing the essential distributed parameters while maintaining simplicity and clarity in calculations, thus making it easier to communicate and share results among engineers and researchers.
And it is on that note that we can draw an equivalent circuit for a nominal Pi transmission line, where here is the sending end voltage Vs and here is the sending end current Is.
Again, looking at the equivalent circuit there, we have two nodes here, which are denoted node A and node B. So at node A, the current I1 flowing at this point will split in such a way that the current flowing to the capacitor will also flows to the impedance, respectively. At the capacitance here, the current flowing is denoted ICS, while the cap value will be half of the total capacitance, C all over 2.
Now the resistance of the impedance will be denoted as R, and the inductance denoted as XL. Again at point B, the current will split into two, where the current flows to the capacitor and the load simultaneously. At the capacitor, the current flowing through the capacitor is ICR, and the capacitor is denoted the total capacitance of the line all over 2, which is C all over 2, while the current flowing to the load will be the receiving end current IR. Finally, the voltage at the load end is known as the receiving end voltage, VR.
Now we can easily derive the phasor diagram for a nominal Pi line using our equivalent circuit diagram there. So when we make VR as our reference phasor here, and because the receiving end load is usually an inductive load by nature, then the receiving end current IR will lag behind voltage and it will be drawn like this, while the current flowing through the capacitor at the receiving end ICR will be leading and also will be drawn like this too. So we can shift this here. The summation of the receiving end current, IR, plus the current flowing through the capacitor at the receiving end ICR will equal to the current flowing through the circuit I1.
Likewise, the same can be applied to node A. That is, the current flowing through the capacitor at the sending end ICS will be leading the voltage and drawn here. Also, this can be shifted here. So the summation of the current through the circuit I1 plus the current flowing through the capacitor at the sending end ICS will equal to the sending end current IS.
Also at the receiving end voltage VR, the current flowing through the resistance I1R will lag behind the receiving end voltage, and it will be drawn like this here, while the current flowing through the inductance of the line I1XL will be drawn here. The summation of the receiving end voltage VR plus the current flowing through the resistance I1R and the current flowing through the inductance of the line I1XL will equal to the sending end current Vs.
Looking at those diagrams there, then we can use them to prove our formulas. So the voltage at the receiving end VR bar will equal to VR at an angle of 0 degrees, equation 1, while the receiving end current IR bar will equal to IR at an angle of minus 0 degrees, equation 2. Again, it is worth noting that this is due to the fact that our load at the receiving end are usually inductive by nature.
Now when we apply Ohm's law at point B, then the current flowing through the capacitor at the receiving end ICR will equal to the receiving end voltage VR all over minus JXC all over 2. This will further be J multiplied by the receiving end voltage VR bar all over 1 over omega C. This will all equal to J2 omega C multiplied by the receiving end voltage VR bar, equation 3.
Also at node B, when we applied Kirchhoff's current law there, then the flowing current I1 will equal to the current flowing through the capacitor at the receiving end ICR bar plus receiving end current IR bar, equation 4.
Likewise, when we applied Kirchhoff voltage law at node A, then the sending end voltage Vs bar will equal to receiving end voltage VR bar plus the flowing current I1 bar multiplied by impedance bar. Equation 5. Again, it's worth noting that Z bar is the series impedance of the line, so Z bar will equal to resistance R plus J inductance X, equation 6.
Just like how we proved for the current flowing through the capacitor at the receiving end in equation 3, the same can also be done for the current flowing through the capacitor at the sending end ICS. So ICS will equal to the sending end voltage, Vs bar, all over minus J XC all over 2. These will equal to J sending end current Vs bar all over 1 and all over 2 omega C. This will equal to J2 omega C Vs bar, equation 7. Also, we can repeat equation 4. This time we are going to prove for the sending end current IS bar, so we can apply Kirchhoff current law at node A. The sending end current IS bar will equal to the current flowing through the circuit I1 plus the current flowing through the capacitor at the sending end ICS. Equation 8.
To calculate the voltage regulation of the line, we will use the approximate method. The receiving end voltage VR will equal to the absolute of Vs minus the absolute of VR all over the absolute of VR multiplied by 100. However, in order to find the exact calculation for voltage regulation of the line, then we will be using the ABCD parameter of a transmission line using the nominal pi method. These will be looked at in the coming series.
The efficiency of the transmission lines can be analyzed like this. That is, the receiving end power PR in 3 phases, all over the sending end power PS in 3 phases. This will equal to 3 multiplied by the absolute of the receiving end voltage VR, multiplied by the absolute of the receiving end current, IS, multiplied by the angle at the receiving end, all over 3, multiplied by the absolute of the sending end voltage Vs, multiplied by the absolute of the sending end current IS, multiplied by the angle at the sending end. Also, another accurate way can be seen here.
Now, we can use those formulas there to solve the following problem. A three-phase 50 Hz transmission line has resistance, inductance, and capacitance per phase of 12 ohms, 0.18 Henry, and 1.25 microfarad respectively. The transmission line delivers loads of 60 megawatts at 132 kV at 0.85 power factor lag. Determine the efficiency and the regulation of the line using Nominal Pi method. So looking at the question there, we can now begin to extract our data. So frequency will be equal to 50 Hz, resistance is equal to 12 ohms, inductance is equal to 0.18 Henry, capacitance will be equal to 1.25 microfarad, the power at the receiving end PR is 60 megawatts, the receiving end voltage VR is equal to 132 kV, and lastly, the power factor is equal to 0.85.
Now we can analyze. The receiving end voltage VR is equal to 132,000 divided by root 3. This is equal to 76,210.23 volts at an angle of 0 degrees. For the load current IR, this will equal to 60 megawatts divided by 3 multiplied by 76,210.23 volts multiplied by the power factor, which is 0.85. This will equal to 308.74 amperes. In order to determine our phase angle, we'll use the cos inverse of the power factor, so our current will be 308.74 amperes at an angle of minus 31.78 degrees.
The impedance of the line can be calculated also. Again, we know that impedance is equal to resistance plus j omega L. That is, 12 plus j open bracket 2 times pi times 50 times 0.18, all equal to 12 plus j, 56.54. And when converted to polar, then our impedance will be 57.79 at an angle of 78.017 degrees. Also, the current flowing through the capacitor at the receiving end ICR can also be calculated. So ICR is equal to J2 omega C times VR bar. When we slot our value in, we will have this here, which will be further equal to this here, and when we multiply both, our final value will be 14.960 amperes at an angle of 90 degrees, which is because in capacitor, current leads voltage by 90 degrees.
Now, the current flowing through the line I1 can be gotten too, so I1 is equal to ICR plus IR. 14.96 at an angle of 90 degrees plus 308.74 at an angle of minus 31.78 degrees. However, in order to be able to add them both, then we'll need to convert from polar to triangle. When converted, we will have this here. So the summation of both will be 262.45 minus j, 147.94. And when converted to polar form, then the current flowing through the line will be 301.274 at an angle of minus 29.40 amperes.
Now that we have all the basic parameters we need, we can calculate the sending end voltage Vs. So Vs will equal to VR plus I1 ZID. So we can slot our value in, and we will have this here. And further simplification, we will have this here. Again, in order to add them both, we will convert from polar form to triangle form, and we will have this here, which is equal to 87,720.206 plus J 13063.317. And converted to polar form, 88,687.56 at an angle of 8.47 volts.
In the same vein, the sending end current can also be calculated. So the sending end current, IS, will equal to the flowing current, I1, plus the current flowing through the capacitor at the sending end, ICS. So we can have this. While we can calculate for J2 omega C plus sending end voltage Vs bar, this will equal to 17.409 at an angle of 98.47 degrees. Now we can add both together, but before we can be able to add them, we will need to convert from polar to triangle form. When converted, we will have this here. So the summation of both is 259.91 minus J130.671. When converted from triangle to polar form, our sending end current will be 290.99 amperes at an angle of minus 26.69 degrees.
The line regulations can be gotten too. The absolute of the sending end voltage Vs minus the absolute of the receiving end voltage VR, all over the absolute of the receiving end voltage VR times 100. When further simplified, we will have this here, and the resultant of this will be equal to 16.37%.
Finally, the line efficiency can be calculated also. That is the receiving end power PR all over the sending end power PS times 100.
But before we can go ahead, we'll need to calculate the sending end power. So we will combine the angles of both the sending end voltage Vs and the receiving end current Is also. So we can have this phasor diagram here. When combined, the summation of both will be cos 35.161, which is equal to 0.817 lagging. So we can have this equation for the sending power, which will equal to 63 megawatts. Now, when we divide them, our line efficiency will be 94.88%, and that is for today's series. In the coming series, we will be analyzing a nominal pi transmission lines using ABCD parameters. Until then, peace.